Assalamualaikum warahmatullahi wabarakatuh. We are group 19. Today, we're gonna present to you chapter 7 memory management from page 41 to 65. Enjoy our presentation.
Memory protection implemented by associating protection bit with each frame to indicate if read-only or read-write access is allowed. Can also add more bits to indicate page execute only and so on. Valid-invalid bit attached to each entry in the page table. Valid indicates that the associated page is in the process logical address space and is thus a legal page. Invalid indicates that the page is not in the process logical address space, or use PTLR. Any violations result in a threat to the kernel. Suppose, for example, that in a system with a 14-bit address space 0 to 16,383, we have a program that should use only addresses 0 to 10,468. Given a page size of 2 KB, we have the situation shown in the slide. Addresses in pages 0, 1, 2, 3, 4, and 5 are mapped normally through the page table. Any attempt to generate an address in pages 6 or 7, however, will find that the valid-invalid bit is set to invalid, and the computer will track to the operating system. Notice that this scheme has created a problem because the program extends only to address 10,468. Any reference beyond that address is illegal. However, references to page 5 are classified as valid, so accesses to addresses up to 12,287 are valid. Only the addresses from 12,288 to 16,383 are invalid. This problem is a result of the 2 KB page size and reflects the internal fragmentation of paging. One copy of read-only reentrant code shared among processes, that is text editors, compilers, and Windows systems. Similar to multiple threads sharing the same process space, also useful for inter-process communication if sharing of read-write pages is allowed. Private code and data. Each process keeps a separate copy of the code and data. The pages for the private code and data can appear anywhere in the logical address space. Consider a system that supports 40 users, each of whom executes a text editor. If the text editor consists of 150 KB of code and 50 KB of data space, we need 8,000 KB to support the 40 users. If the code is reentrant code or pure code, however, it can be shared, as shown in the slide. Here, we see 3 processes sharing a 3-page editor, each page 50 KB in size. Each process has its own data page. Reentrant code is non-self-modifying code. It never changes during execution. Thus, 2 or more processes can execute the same code at the same time. Each process has its own copy of registers and data storage to hold the data for the process execution. The data for 2 different processes will, of course, be different. Only one copy of the editor needs to be kept in physical memory. Each user's page table maps onto the same physical copy of the editor, but data pages are mapped onto different frames. Thus, to support 40 users, we need only one copy of the editor, 150 KB, plus 40 copies of the 50 KB of data space per user. The total space required is now 2,150 KB instead of 8,000 KB. Structure of the page table. Memory structures for paging can get huge using straightforward methods. Consider a 32-bit logical address space as on modern computers. Page size of 4 KB, page table would have 1 million entries. If each entry is 4 bytes, 4 MB of physical address space over memory for page table alone. That amount of memory used to cost a lot. Do not want to allocate that contiguously in main memory. In the next section, we explore some of the most common techniques for structuring the page table, including hierarchical paging, hash page tables, and inverted page tables.
Hierarchical page tables. Break up the logical address space into multiple page tables. A simple technique is a 2-level page table. We then page the page table. 2-level page table scheme. So this is the outer page table and this is page table, and this is memory. So from the outer page table, it will mapping to the number in the page table, and from the page table, it will mapping to the memory. Two-level paging example. A logical address on 32-bit machine with 1K page size is divided into a page number consisting of 22 bits, a page offset consisting of 10 bits. Since the page table is page, the page number is further divided into a 12-bit page number, a 10-bit page offset. Thus, a logical address is as follows. Page number, and this is the page offset. We will show with the P1, P2, and D. So where P is an index into the outer page table, and P2 is the displacement within the page of the inner page table, known as forward map page table. From left, it is non-inverted page table. So the logical memory of process P1 will then map to the page table of process, and then will map to the physical memory. From right, it is the page table which is inverted. So from physical memory will map to the page table, and then will map to the logical memory of process. Address translation scheme. In the logical address, which is P1, P2, and D, P1 is an index into the outer page table, and P2 is the displacement within the page of the inner page table, which is known as the forward map page table. So the P1 will go to the outer page table, P2 is end of the inner page of page table, and followed by the D.
64-bit logical address space. Even two-level paging scheme not sufficient, if page size is 4 KB, 2 power of 12, then page table has 2 power of 52 entries. If two-level scheme, inner page tables could be 2 power of 10 4-byte entries, address would look like this: P1 as outer page, P2 as inner page, and D as page offset. Outer page table has 2 power of 42 entries, or 2 power of 44 bytes. One solution is to add a second outer page table, but in the following example, the second outer page table is still 2 power of 34 bytes in size, and possibly 4 memory access to get to one physical memory location. Three-level paging scheme. Here is the example. The first diagram, we can see P1 as outer page, P2 as inner page, and D as offset. And the diagram below, we can see P1 as second outer page, P2 as outer page, P3 as inner page, and D as offset. Next, we move to hash page tables. Common in address spaces more than 32 bits, the virtual page number is hashed into a page table. This page table contains a chain of elements hashing to the same location. Each element contains, first, the virtual page number, second, the value of the map page frame, third, a pointer to the next element. Virtual page numbers are compared in this chain searching for a mesh. If a mesh is found, the corresponding physical frame is extracted. Variation of 64 bits addresses is clustered page tables, similar to the hash, but each entry refers to several pages such as 16 rather than 1. Especially useful for sparse address spaces where memory references are non-contiguous and scattered. The algorithm of hash page table works as follows. Firstly, the virtual page number in the virtual address is hashed into the hash table. Second, the virtual page number is compared to the field first in the first element in the linked list. Third, if there is a match, the corresponding page frame field is used to form the desired physical address. And fourth, if there is no match, subsequent entries in the linked list are searched for a matching virtual page number. Inverted page table. Rather than each process having a page table and keeping track of all possible logical page, track all physical page. One entry for each real page of memory. Entry consists of the virtual address of the page stored in the real memory location with information about the process that owns that page. Decrease memory needed to store each page table, but increase time needed to search the table when a page reference occurs. Use hash table to limit the search to 1 or at most a few, page table entries TLB can accelerate access. But how to implement shared memory? One mapping of a virtual address to the shared physical address.
So this is diagram of inverted page table. To illustrate this method, we subscribe a simplified version of the inverted page table used in the IBM RT. IBM RT was the first major company to use inverted page table, starting with the IBM System 68 and continuing through the RS over 6000 and the current IBM Power CPUs. For the IBM RT, each version address in the system consists of a triple, process ID, page number, and offset. Next, Oracle SPARC Solaris. First, consider modern 64-bit operating system example with tightly integrated HW. Goals are efficiency and low overhead. Second, based on hashing but more complex. And third, 2 hash table, 1 kernel and 1 for all user process. Each maps memory address from virtual to physical memory. Each entry represents a contiguous area for mapped virtual memory, more efficient than having a separate hash table entry for each piece. Each entry has base address and span indicating the number of pages the entry represents. Third, TLB holds translation table entries TTEs for fast hardware lookup. A cache of TTEs reside in a translation storage buffer TSB, includes an entry per recently accessed page. And last, virtual address reference cost TLB search. If missed, hardware work the in-memory TSB looking for the TTE corresponding to the address. Is mesh found, the CPU copies the TSB entry into the TLB and translation completes. If no mesh found, kernel interrupt to search the hash table. The kernel then creates a TTE from the appropriate hash table and store it in the TSB. Interrupt handle returns control to the MMU, which completes the address translation. Next, the example of the Intel 32 and 64-bit architecture. First, dominant industry chips. Second, Pentium CPUs are 32-bit and called IA32 architecture. Next, current Intel CPU are 64-bit and called IA64 architecture. And last, many variations in the chips cover the main idea. So this is the example of the Intel IA32 architecture. First, supports both segmentation and segmentation with paging. Each segment can be 4 GB. Next, up to 60K segment per process and divided into 2 partitions. First partition of up to 8K segment are private to process and keep in local descriptor table. Second partition of up to 8K segments share among all process and keep in global descriptor table. Next, CPU generates logical address selector given to segmentation units and which produce linear address. Next, linear address given to paging unit which generate physical address in memory, and paging unit form equivalent of MMU, and last, page size can be 4 KB or 4 MB. So this is diagram of logical to physical address translation in IA32. In this section, we examine address translation for both IA32 and X66-64 architecture. So before we proceed, it is important to note that because Intel has released several versions as well as variations of its architecture over the years, we cannot provide a complete description of the memory management structure of all its chips. No, we can provide all of the CPU details as the information is best left to books on computer architecture. Rather, we present the major memory management concept of this Intel CPU.
Next, the Intel I will talk about the Intel IA32 segmentation. First, in the Intel IA32 segmentation, we have the logical address, in which the logical address is divided into two parts, which is the selector and the offset. The selector will go into two ways, which is the descriptor table and the segmented descriptor. Else, the offset will go to 32-bit linear address. Next, in the Intel IA32 paging architecture, we have the page directory, in which the page directory will go to the page table, and through page table it will go to the 4 kilobyte page. And the other route that the page directory take is to straight to the 4 megabyte page. Next, I will talk about the Intel IA32 page address extensions. The 32-bit address limits let Intel to create page address extension (PAE), allowing 32 bits access to more than 4 GB of memory space. Paging went to a 3-level scheme. Top 2 bits refer to page directory pointer table. Page directory and page table entries move to the 64 bits in size. Net effect is increasing address space to 36 bytes to 64 GB of physical memory. Next, the Intel 86 to 64. Current generation Intel 86 architecture, which is our current generation. The 64 gigs is ginormous, which is greater than 16 exabytes. In practice, only implement 48-bit addressing, in which for page sizes of 4 kilobyte, 2 megabyte, and 1 gigabyte, and 4 levels of paging hierarchy. And can also use PAE, so virtual addresses are 48 bits and physical addresses are 52 bits. Then the example, which is the ARM architecture. The dominant mobile platform chip, which is Apple iOS and Google Android devices, for example, modern energy efficient, which is 32-bit CPU and 4 kilobyte and 16 kilobyte pages, and have 1 megabyte and 16 megabyte pages, the term sections, and the one leveling paging for sections, the 2 level for smaller pages, then the 2 levels of TL bits, in which the outer level has 2 macro TL bits, 1 data, 1 instruction. The inner is single main TLB. The first inner is checked, on miss outers are checked, and on miss page table work performed by CPU.